And not only did he give me a PowerPoint, oh my God, it was great. Fantastic. No. At least let me finish the first one. I mean, I did finish it. Some of you
Okay, let's try to start. First of all, I want to say that in terms of the office hours, I sent a couple of announcements earlier today for you to see what the rooms are for the office hours for the TAs and for me. And it was just confirmed that the room number that I had and the times for my office hours now are, the rooms have been confirmed. So we'll start this, well, you can take advantage of the office hours from the TAs on Friday. And then next week, the plan is gonna run, you know, as it is on the syllabus. Also, I've been looking for a room for the problem-solving sessions. And what I understand is there are many of you have conflicts from 5 to 7 on Tuesday. And so I try to find, I'm looking for an earlier time, 12 to 1, sometime between 1 and 3, and 3 and 5. And the only problem we have so far, with the exception of the 12 to 1 time, is that the rooms that are available are very small. So the largest we were able to find was 40. But I will try even, well, we will have one next week. So between now and next Tuesday, I will try to look for as a big of a classroom as I can. But that's where we are. Now, usually in those problem-solving sessions, not everybody shows up, but I would suggest if, because there are always conflicts with anything that we do outside of this class. The only conflicts that have been resolved, have mostly been resolved, are the ones around this class, the lectures. Anything else will have some of you with conflicts. My advice is that you stay in touch with your team. Make sure that one member of your team comes to the problem-solving session, takes notes, and then, or make comments, and then they can share with the rest of you. All right, that will be something that I would suggest. If nobody shows up from a team, then try to make sure that you get the information available. I'll do the best I can to put the solutions on Canvas. Sometimes we do problems that, you know, just because we are working with the students, and then I will try to do the best I can to give you all the information from those sessions. But I'm just saying that you may have to make sure that at least one person from your group comes. But I will let you know as soon as we find the room. And so we'll start next week. Any questions about office hours and about the problem-solving session? Okay. Have you found the material that I put for the previous lecture and today's lecture on Canvas? Sometimes I do put material for today's lecture not too many hours in advance, but at least the material for the previous lecture, everything is there. Whatever we have done in class, whatever notes I have on my own, I place them on Canvas. So make sure that you look at them, use them, in your studies and homework problems. The first homework you are going to receive will be this Sunday. All right, this Sunday. And it's going to do next Sunday. So you're going to be able to do the homework next week with your own team, the team that you have right now. And you're going to be able to take advantage of all of the office hours. So don't wait until the last moment to solve the problems in the homework, all right? So if you have any questions, you can use my office hours, the TA's office hours, before you submit the solution on the following Sunday. Any questions? Okay, so up here is the outline for today's class. I always like to start with a summary of what we discussed, and it's going to be a short summary, obviously. And then we'll talk further about conductors in electrostatic fields, electrostatic shielding, and then the image theory. Okay, and all of these for charges that are in free space. We have not introduced any dielectrics yet, and that is going to happen in the next chapter that is going to start next week. Okay, so what did we talk about last time? We introduced the electric potential, which is a scalar and is given by this. We derived it from here, that the electric field vector, and this is intensity, obviously applied at one point in space, is the gradient, negative, of this scalar, which we called the potential. What do we call the difference between two potentials? Voltage, exactly. And we said that a gradient is nothing else but theta x in the Cartesian system, and then you can convert it to any other system. And then I have given you the conversion formulas, all right? So you should be able to convert. Now, from here, so this is the differential form that defines V. There is an integral form that defines V and is derived out of here, and the integral form goes like this. It talks about the voltage here. It's the difference between two potentials. A potential B, point A. And that's the negative of the line integral between these 2 points, and make sure that the order is correct, because otherwise if you flip the order of A and B, then really you have to take care of that in the sign. All right, so don't flip the order, don't use the order arbitrarily, but always keep the negative sign, because that's going to give you sometimes a wrong formula, depending on how you place A, B's. So I went up. All right, so that's the integral form, that's voltage. This is the differential form, that's potential. And what is VBA? The potential at B minus the potential at A. That's the formula. Then what else did we talk about? Gauss's law. So Gauss's law relates the electric flux density, D, and I will define this first. D is nothing else but epsilon naught, which is the permittivity of free space, with times E. Or E is D divided by epsilon naught. And then what did Gauss' law say? That the divergence of D is rho sub V if we are in a three-dimensional space, where rho sub V is the charge density. If it's three-dimensional, it's going to be a volume charge density. What does that mean? It's going to be Q per meter cube. If we are in a two-dimensional space, it's going to be surface charge density. It's going to be what? Coulombs per meter square. And if we are in a one-dimensional case, that will be a line charge density. It's going to be coulombs per meter. Now, you can be in a three-dimensional space and have one line charge. Okay, so your problem is going to be 3D, but your source, which is the charge in this case, is going to be a line source. If you can be in 3D and have a surface charge distribution. So all of your charge is only on one surface. So your source, which is the charge, is going to be a surface charge. All right? And in this particular case, since we are looking at one point, in the most general case, we assume it's a volume charge density. So this one. And what is the integral form of this? We use the divergence theorem. So we integrate it within a volume V. So we found a volume V that has the charge distribution. This is volume V. And then this volume has a surface, S. The surface of the volume is a scalar. The surface of the volume is a vector. Why is that? Because it has a direction. And this vector has this as the unit vector, which is always perpendicular to the surface. Okay, so we found that this closed surface integral of d dot ds, all right, so the vector of the surface comes here, equals the total charge q inside the surface that is enclosed by the surface. Okay, so that's what we discussed last time. Okay. Having said that, I would like to ask you to do a problem on the basis, it's going to be focusing on this, and then we'll talk a little bit about that. So I will give it to you on Top Hat for a moment. Okay. All right, so let me present the problem. Okay, this is a problem from the book, and it gives two functions, a triangular function and a pulse function, all right? And it says that if one of them is to be a function for rho sub x, it says here. So we have one d charge and a field distribution. The density of a volume charge in a region of free space depends on the Cartesian coordinates x only, obviously. Which of the following combinations of the two periodic functions f1 of x and f2 of x shown in figure 120 can represent the charge rho of x and the associated electric field density E of x? So if the charge is the first one, is the electric field the second? If the charge is if the charge is the first one and the electric field is the second, is that a correct answer? That's A. The second option is that the charge is the second function and then the field is the third. Is that the correct one? And then it gives two more. All right? So that is excuse me, I said that. It was not that. That is an application of Gauss's law. And so let's try to solve it. You will have, I will assign it, and you will have 5 minutes. Just a second. I have not assigned it yet. It's going to be from the time I assign it. Wait a second. Yes. Pardon me? I will assign it in a second. What do you mean I closed? Yeah, because I will assign it. I have not assigned it yet. Wait a second, I need to put a timer. I have not assigned it yet. One moment. Okay, I'm assigning it right now. Homework. Okay, fine. Sorry. Homework. Okay. I hope you see it on your own because I need to. You have 2 more minutes. All right, so you have half more minute. I gave you 30 seconds. I gave you 1 more minute. So you guys, please enter whatever you have. Those who have not entered it yet. All right? Enter whatever you have. That's okay. I'm ready to unassign it. Is it okay? I'm going to unassign it. Okay. Oops. Ah. I don't seem I can unassign it. Uh-huh. You know, I cannot unassign it, which is fine, for whatever reason. I click on it, but nothing happens. So let's see. Unless I don't have connection. Ah. Okay. So if I want to show correct answer, so that's what it is, and we'll talk about it. Oops. That's the one, all right? Okay, let's talk about it. It says there that we have an one-dimensional charge. And that we have, it has simplified the problem, all right? We have one-dimensional charge. What does it say? Let me go here. It says that free space, only x coordinate. That's one-dimensional problem, first of all. In a one-dimensional problem, E and every other entity will be function of only one variable, x, only one coordinate, x. And therefore, both E and rho are function of x. What is then this? How is this then formula becomes in one dimension, in a one-dimensional problem? This is going to become what? Theta. And this is divergence. All right, let me just write the general form, equals 1 over epsilon naught, free space, rho of x. And let's just assume that we have only one component in the electric field. For simplicity, is this sub x. And so we make it theta x, E of x equals 1 over epsilon naught rho of x. So what is the relationship between E and rho? That the derivative of E is this function. So you have to decide from these two functions which of the two is the derivative of the other. So which of the two is the derivative of the other? Exactly. F2 is the derivative of F1. So what is the charge and what is the field? The charge is the derivative of the field. Therefore, the charge is going to be F2 and the field is going to be F1. That's how it is. Okay? Yes? It does not give you a function F1, it does not give you an amplitude. See? It only gives you how it changes versus x. So of course the amplitude has to be such that it follows this formula. But it does not give it there. Otherwise, if it had given you an amplitude and it was not exactly that, then probably none of the answers will be the correct one if the others had remained the same. Okay? Any questions about this? Okay. Then let's move on. So now we are going to talk about conductors in electrostatic fields. And I have a very simple example, first of all. So we have, let me erase all of these. So let's assume that we have a uniform electric field, and let's assume that it goes along the z direction. Okay, so if we are in, I will put here, assuming that we have this coordinate system, x, y, and z, somewhere here. Let us assume that we have a field that goes along z, and it's uniform. The lines of the electric field lines are parallel. All have the same direction, all have the same value. All right? Constant. Let's assume that E is E naught along the z direction. Then you may say, does a field like that exist? Yes, exactly. Where does it exist? And yes, capacitor is one. The other is where? Yes? But that's not electric. Inside the solenoid, what we have? Magnetic. Where else is it? But it has to be an ideal solenoid. But where else does a field like that exist? In the far field of an antenna. It's called a plane wave. All right? Because if I have a little antenna here and radiates in free space like a balloon, all right, on a sphere, if you go very far away from the antenna, what you're going to see is something like that. So we call it a plane wave. So in reality, it does exist. And of course, the capacitor. Okay, let's assume now in this one that I bring a, this is infinite, right? Extends everywhere. And I bring an infinite conducting slab. Very thin though. So it goes like this, but I will give it a thickness so we can talk about what is happening. So I bring an electric, a conducting slab. It's all metal. All right, so it's a conductor. So what happens inside the conductor? Do you know? When we bring it in an electric field? Is there an electric field inside the conductor? Why? Can somebody tell me? It's zero. Why? Let's assume that you have this conductor. Let's solve that problem first. And I put that in this magnetic field, electric field, excuse me. So what is going to happen to it? What is a conductor? What is the characteristic of a conductor as a material? Is a material that has what? Plenty of what? Free electrons. What does that mean? Nothing is free. But there are electrons that are not bound very strongly to the nucleus. So a little bit of energy that the electric field is going to bring, it excites them, so they leave the nucleus. All right? They leave the atom, I should say. And then they just ready to fly everywhere. A little bit of energy, even some heat sometimes makes them, you know, go left and right. Now, if there is no electric field, all of these free electrons go in all different directions. They have no orientation, so they hit with each other. And then eventually nothing happens. There is no current, there is nothing. All right? However, when you put an electric field, these electrons are negative charges, but the atoms they leave behind, what do they become? Positive. Because the atom by itself is neutral in terms of a charge when everything is balanced. But when an electron leaves, then it becomes positive. So then you have positive and negative charges, all right? And so if the electric field outside goes like that, then all of the charges here, the positives, will under the force, so all of the charges will feel force. Okay? And they are going to move like this, and the negative will move like that. So then you're going to have a depletion of charges in the middle, and you're going to have charges like this here. And they will be, of course, if the material is to be neutral, have no charge, the number of positive charges up has to be the same with the number of negative charges down. What happens if you have positive and negative charges on two sides and they radiate in here? It cancels out. All right, so there's nothing there. In terms of an electric field, inside is nothing. But outside, there is an electric field. So these charges here, when they come, they're going to sustain this electric field, all right? So they're going to be here after you place the metal, and they will sustain a similar electric field. They're not going to change it, especially if I place this metal in this way, that it's perpendicular to the lines. So the charges will not perturb the direction of the electric field, but according to other conditions may perturb the value. All right, so these lines that you knew before will be replaced above with those here. And those will be also uniform, same direction. So if I am here, I will not necessarily feel the difference in the direction of the field. That's not true about the value, but in the direction of the field. What happens underneath? They will create this. All right? So here. Here. And what else is characteristic about those charges, both here and there? So we have a new electric field right now, but the direction is the same. And the way it is as if the field has not been perturbed by the metal, this field. All right, the way we place the metal there. However, the field inside the metal is 0. Okay, 0 here. The other characteristic is because of the type of the problem, so the initial field was infinite long, the slab that I placed there is infinite in that direction, uniform in terms of its thickness. And because I placed it perpendicular to the lines, then the charge distributes evenly everywhere. And of course, it's flat, does not have any anomalies, does not have any peaks or valleys here on the surface. All right? So the charge distributes uniformly. Okay. Let's assume now that I have the same field initially. And then I put the same slab, but with an angle. So I do this. What is going to happen then to the initial field? Let's discuss that. What do you think? What is it that we know? That the electric field inside here is 0. And we also know that the charges, since this is uniform, uniformly distributed, that the charges here will be uniformly distributed. All right, because the value of the field, you saw it's constant, independent of z, independent of any other coordinate parameter. So then here you're going to have the positive charges and then here what are you going to have? Negative charges. Okay, now let's see what those charges will do. This is the initial field, all right? So I will just do it like that. Eventually, we're going to eliminate it. Tell me, what is going to happen to this to the electric field on the surface of the slab? Is it going to stay like that, like it was before? Exactly. It's going to bend to be perpendicular. And then it will have to align itself like this. Okay? And then here is going to bend to be perpendicular. And the same here. Now, and then I will come back to another question I have. And then here the same. All right, so the field here has to be like that, and then it will have to be like this. All right? So there is a disturbance of the initial field, of course in the value, but also in the direction, because always, since the metal has zero electric field, what does that make the potential on its surface? If it's a zero electric field everywhere on the surface, what happens to the potential? Constant, all right? It may be zero if it's connected to a ground or something, but it's not necessarily zero. It's going to be constant, however. Okay. What if now here we have the same initial field, constant, like this, but in there, instead of an infinite slab, we introduce a square conductor, like a box. And I will show it only in 2 dimensions, all right? Something like that. And it's all metal. So what happens inside? No electric field. So we remove that. Okay, then what is going to happen on its surface in terms of the, let's start with the charges. What is going to happen with the charges? Of course, they will polarize because of that. Okay, so the positive charges will try to go up, and the negative charges will try to go down, obviously. But are they going to distribute uniformly? Why? So what we have learned, all right, from previous courses is that the charges will tend to go to the places that have corners, you know, like peaks, like sharp edges and so forth. They will try to concentrate in places where the surface of the metal changes abruptly. Why is that? Let's draw it first, and then I will ask why. I mean, we know that, most of us, all right? There is always this. Do you remember these experiments they do in physics where they put somebody off the ground and they apply a charge and then everything goes into the hair? You have seen that, all right? They do it in high school. They do it in the early physics classes. Same kind of thing. It goes, the charges go to the sharpest edges of the object that carries them. So here you're going to have the positive charges. And then you're going to see more positive. Now, let me not do the round thing because it takes too much space. So it's going to positive charges here. And then you're going to have many here. And then you're going to have many here. And then negative charges here. And then many negative here. Okay, so what is going to happen? We are going to see some of the lines coming here, here. And then here we're going to see some lines, not exactly, like going like this. All right, and here. And then at some point, we'll go like out of here like this. And the density of this line shows that the value of the field is higher. So that's what you're going to have. All right. So these lines are gone now. They have been modified. Okay, that's what we've known. Let's try, however, to understand a little more rigorously why this is happening here. Why do charges go to the sharp corners? Do you remember what we said? What is the relationship between a charge and a field? Let's talk about that. What is the relationship between a charge and a field? Let's look at it. The charge is the divergence of the field. And what does the divergence of a vector show? What does it show? How fast the vector, if it's a large number, how fast or how slow the vector changes in space. That's what a divergence shows. All right? So here, see what happens. Because of the metal and this direction, always the electric field has to be 0 on the surface, which means that as we go very, very close to this edge, there is going to be an abrupt change in the direction of the electric field, because right before the edge, this component has to go to 0, right before the edge. Right after the edge, this component has to go to 0. For the electric field to change from this, up here, this component is non-zero, and down here, this component is non-zero. Did you understand what I'm saying? When the tangential component on the metal goes to 0, the vertical, the normal component, gets its largest value. So here, the largest value goes to this component for the electric field, and on the other side, right there, goes to this one. And that is happening. The electric field changes from this to that over a very short space. So the change, the divergence of the field right here is extremely high. All right? The divergence of the field is going to become very high. So the rate of change of the field there is very high in relation to space, which means then this is going to be very large. That's why, all right, the charges go there. Or you can consider it to be the reverse, and you can say, depends on how you want to explain it. You can say the charges will go there. That's another explanation. I will give you two different. The second explanation is to prove that the charges will go there, and then, of course, the field has to change very abruptly. But so you can base this explanation on the force that the charges will feel. A charge that feels a very high force will try to go as far as it can get until it hits a really a wall. The wall is at the end of the metal, all right? And it's going to try to go as far as it can along the direction of the electric field, not along any arbitrary direction. So the charges here, from moving from the center to that, will eventually crowd at this corner, which then tells you, because of that, that the electric field is going to feel a very high, large change over this very small space. So this is exactly how we can explain why charges go there. All right, so on the basis of that, then we can do, what time is it? We can do one more problem, and then we'll take a couple of minutes break, and then we'll go to the next hour. Okay, let me go back to top hat. All right. Now it's going to be based on these concepts that we discussed, these concepts. Okay. Okay, this one from the book again. So this one says the following. So we have like a capacitor, you see it, but minus Q is up, all right, you noticed? On this one, negative charge up on the upper plate, positive charge on the lower plate. And then in there we place a metallic slab. And then it's asking you to find the right answer to the question. And what is the question? That, let me see, read. Electric field in region 3 is 0. That's one possible answer. Electric field in region 3 is minus E0. The third is like 1/3 of E0. The fourth is 2/3 of 3/2 of E0, and the last is E0. So this is the question. You will have to do that considering how the charges go. All right, remember? That's how you're going to find it. Think how the charges will be distributed inside the slab, and then you will find from there what it's going to be. Okay. I will assign, ready to do it? 5 minutes? All right, we'll assign it. 5 minutes. And then you can see it. Can you see it there? So I can remove mine because it shows who responds to what. Okay. That is an infinite slab. Okay, infinite structure only along the other direction. So it's an infinite slab is inside an infinite electric field that's sustained by two conductors.
I think it seems like it's being the same thing.
In that field, right? You're gonna chase it.
The length of the vector doesn't change the straight direction.
So if it doesn't change it, that's like gut reaction too. So like this is finite and not infinite. It's not infinite. So that's like the only thing. But why would it change? Right? This is exactly what's on that, not the other way around. No, but then if you have a dielectric, it does change.
Scotto stream there. That would accept it. Nah. I feel like all of these answers are always like trick questions. You know what I mean? It's the same thing as before. You have the negative. No, put this in there and the same thing. It's positive on top. But what do you think down there? Here's a guess. What do you think? That's what I'm looking at. You think electromotion? Otherwise, make it really far apart. Like, strength is
Okay, I'll give you 1 more minute. How about that? One. I mean, we're already at 8 minutes right now. So one more.
I don't know.
All right, I'm going with my gun. But no,
That's the worst.
Okay, I will then do the following. This is going to be fun. I will turn it, I will unassign it, and then I will show you what we got. I'm not going to tell you what the right answer is yet. There is a split in the class. So which team went for the for D? I would like someone from D and someone from E to explain to me. No, we need to hear it. Listen, and then we'll make a decision which one is the correct one. So I would like to hear, because obviously half of the class went for one and the other for the other. Let's talk. So let me write the problem here. Minus Q, all right, plus Q. I will assume that this is infinite large. You know, we don't have what we call side effects or edge effects. That Q is uniformly distributed, all right, and I will assume that that Q, because it's connected to something, remains constant. So they give it to you, minus Q plus Q, all right, and then we'll assume that the surface charge here is the same, uniformly distributed, negative value here, uniformly distributed positive. Okay, and then we bring inside here the slab. All right. Who would like to say the thinking, what was the thinking for D? Yeah, that's okay. We're not going to take any points out from the discussion.
Wait, it's going down. Wait.
It's going down. Anna said, I kept it up. That's all right. I trust you, then you're not going to change it. So please don't do that. No need. No need. Okay. No need. We don't play for a few points here and there. 1 and 2 points. Trying to do that does not pay. All right? Okay. Which group did D? Raise the hand. Who did D? And then who did E? Did D, E? All right. Let's talk about it. Let's start with D. What was the thinking in this problem? Let us a little bit on what you discussed. First of all, what is the field in here? Okay, that we knew. Okay, let me hear the rest. That was obviously 1/3 of this one. Each one of those is 1/3. I forget about I did not do it exactly. I did not draw it the right way, but it's 1/3. Okay. Remains there. Okay. So the charge here remains that. So what is going to happen here? What are we going to have? Positive what? Positive what? Positive value what? You said it's positive Q? Is that what you said? Yes or no? Okay, positive Q. What happened down here? So this. Okay, now that we have that, how much is the field? Here. E naught. E naught is this one. Okay? And what does that do? It changes what when the distance between the two plates changes? So let's talk about this. This field is constant. All right? It does not matter whether you are here, here, or here. The value of this is going to be a constant. All right? Why is this going to be a constant? And why is it? Because here and here has the same value. Why does it have the same value? Different directions. Because of this. At the surface, the normal component of the electric field at one point in time is rho is related directly to the charge, okay? And is not dependent on the distance from here. It only depends on the charge that creates it, okay? All right, so that we know. The next then, if you have the charge here and there, then the divergence, again, of this new field, let's consider it a new field here, all right, E prime. The divergence of that is what? Let's call it Q, even if, you know, it's not, this is the, let's assume that this is, yeah, we'll call it rho, the same thing, all right? That has not changed, over epsilon naught. Okay? What is, if the electric field is only along the normal direction, let's assume this is the z. Then it's going to be theta, theta z, all right? Equals rho at that point here over epsilon naught. So how much is going to be right at that point? Assuming that it's you can go like, you know, because you are right in the surface. Inside the surface is 0. All of the electric field is 0. Outside of the surface has an immediate value, and then I can write this as delta E over delta Z, all right, because I'm going right here over rho over epsilon naught, which means that the value of the field E above here, let's call it E1, and then E2, E1. E1 is here inside the metal. Let's make that 0. This is, okay, this is, I'm showing the metal here. And this is on the top of it. So by a very small all right, and then it's not exactly like that, because it has to be, there needs to be something else here. So delta E over delta, in any case, let's assume that, just to simplify things, E2 then is going to be a function of rho over epsilon naught. Is not exactly correct. This is an approximation, what I'm saying. Is going to be only dependent on the value of rho at that point in space, on the surface of the conductor. That's what you got. Therefore, how much is this going to be outside here? When this one has this place and that place, has minus Q here, has Q here, minus Q, and Q. How much is going to be here? E naught. Do you understand why? What is going to change in this? If the field remains the same, what really changes? between this and that conductor, this and that conductor. Yes, direction, but what else? The voltage, the potential difference between these two will change because of the distance. That's what changes. The voltage changes, not the electric field. All right? So what is the correct answer? E. So please go home. All right, this is an important question. It's not a difficult one. Just think a little bit. Take it home and go over it. All right, and try to look at it and carefully. Of course, the capacitance is going to change. Why is the capacitance going to change? Because it relates to V. And V changes here. All right, so the capacitance absolutely will change. And we'll talk about the capacitance next. There is another thing that maybe you got a little bit confused. If the charge were to, somebody would come here and tell me that the charge will change, then the field will change. But the charge remain constant. All right? So what happens, I may think why you got a little confused in this one, in terms thinking that the field may be different because of the distance. When you have a field like this, which is parallel, uniform, everywhere has the same direction, everywhere has the same value, everywhere has the same value. So how far you are from the charge is not important. All right, you may be right here and the value is going to be the same, the closest to the lowest charge. You may be up here and the value is going to be the same. You may be in the middle and the value is going to be the same. It does not change for this particular problem. It remains constant. This is an electrostatic problem. In higher frequencies, things are different. But in electrostatics, the value of the field does not change with the distance. It only changes with the value of the charge. What it changes with distance is the potential. All right? And that then, of course, changes other characteristics of this structure. Okay, is that clear? Any questions? Yes?
Earlier, you said when you place a rod in an electric field, it may change the amplitude of the electric field, but it won't change direction. Right? How is that different than this situation where it won't change the amplitude?
So here is what happens in the other case. In the other case, practically, you had this. Let me erase. I'll leave this one. The other case, we had this field, uniform, and we had this one. So what happened is the field here had to change. Originally, the initial field had only one component along the z direction. So E was E naught Z. And here, because, yes?
I'm sorry, I was actually talking about the one with the horizontal rod.
So you're talking about this one. This one. Yes. Okay. The reason I said it may or may not change the value, I did not say it will change it always. I said the direction is going to be the same. In case, what if this rod is, has a voltage somewhere and has more charge in here? All right, if this rod has more charge in here, in addition to what this one has, then it has the potential to change the value of the field. All right, if this rod, for example, let's assume that this is steel. It's a much more general problem than this one, but it's a constant. And let's assume that we had here plus Q, all right, minus Q. And I bring a rod that has a charge on the surface. I have charged it. It's not neutral when I bring it in. All right, see what I'm saying? So it has positive charge everywhere. Because just I put positive charge with a, then the charges have to be redistributed to accommodate for the other field, and that is going to change the other charges. All right, that's why. Thank you. All right, let's now do what? What time is it? All right. So we have one more. This one should be very simple. This is going to be simple. Simple. This is going to come as a gift. I'm telling you. Let's do this one. All right. Here you go. That should be a gift. It says, okay, what you have here is a charge, and then around it you place a neutral, we call it Faraday cage. Faraday cage means it's a metal that is not charged, all right? And it's enclosing the charge, fully enclosing it. So the initial cylinder, if you like, or a sphere, if it's a sphere, it was totally neutral. Then we take this charge and place it inside. And then we place it unevenly, not at the center, unevenly. So what is going to happen to the charges, of course, since this is neutral before, well, and you put it inside a charge, you put it around a charge, is going to disturb the neutrality. And so the positive and negative charges will go places. So it wants to, it asks you, and almost I solved half of the problem with what I said, to pick the correct solution. And I will assign it to you. Okay. Yes, yes.
So when we have, it says induced charges on the outer surface of the shell, that means there's more charge than what they're showing us, right?
What does it say, the problem? It says, yeah, of course.
So
Yes.
even though, like, for this one, we're saying that all the negatives are going to go to the outside because this charge is negative. That means on this inner ring side, there's some positive charge, right?
Let me
Do you
see
see what I
again.
mean?
Yeah, I see what you mean. He says a
I can
negatively
draw.
charged, small body is situated inside an uncharged spherical metallic shell. The distribution of induced charges on the outer surface of the shell. I would assume, in this particular case, that is very thin.
Assume that it's
Very thin.
Okay. Okay. So that the only charge here is the one that they're showing me. There's no
Yes.
charges they're not showing. Because I can make a case for this one or for this one, right? Because if you have this negative charge close to the surface, that means on this inner surface, there's the positive charge, and then the outside is the negative. Or if because the Faraday cage is neutral, there has to be as much positive as there is negative. So I can see
Exactly.
two cases.
So yes, yeah, I would assume that it's thin, very thin
Okay.
at this moment. Okay, so it's extremely thin, and you
Okay.
don't have any other charges you don't see.
Okay.
Exactly what you said.
Thank you.
So what? Also for all of you, the charges you see are all the charges you got. There are no hidden charges in this. Okay, the charges you see are all the charges you got on the shell. There are no hidden charges.
Yeah, that doesn't. No, but why would it be like that though?
Trying to get out.
But it only wants to charge on the outside. Yeah, no, that would give it away. I can't. Are you kidding me? 5 points? A lot's on the line here. But why would it be on the outside though?
Because I think because what happens from the if it's very thin, the charges will at the outer surface, because outside of the cage the field has to be 0. So the way I understand the problem is that this is the charge that you see on the shell. Period. Yeah.
Yeah, no. I don't understand.
It's neutral before, so There is only one possible answer, you mean, in this problem? Yeah.
That's all I meant. But if we're just looking for like balance of charges, I mean like equal positive, like equal charges.
So that shell has to be, if it's a Faraday cage, all right, it has to have a zero. It has to create a zero field outside. So when is it going to create a zero field outside? When but there is no other charge in this. Assume that there is no other charge in this particular problem. That's what I'm saying. Because it wants to, I think, I'm not the author, but I think it wants to help you to think what is going to happen to the outside, not to the inside. I think. Okay. So maybe, it's not a well-defined problem. It could be, but we'll see. Let's see. Let's see how we're going to answer it. Okay, I thought maybe it was too simple, but the devil sometimes is in the simplicity. Okay, I think we had 7 minutes. And that's probably, I will, okay, enter whatever you think at this point, and then we are going to discuss it. And I will unassign it. Okay. And then I will connect it here to show. And I'll tell you what I thought about the problem. So, again, we have a split, almost. Let me tell you what I thought when I read the problem, all right, the way it was presented, and then we can discuss it if you think that my thought was wrong. Wait, be quiet. Thank you. I'm a human being. It is possible that I'm wrong. I've been wrong multiple times. So. Being wrong is not necessarily bad. You know why? Because that's what we learn from. How many times you remember one time when you did everything well, correctly? I don't remember any of those. I only remember those where I messed it up. But in any case, let's think about this problem the way they gave it to us. So it is a charge, and it is a negative charge. All right, and then around it, we place a Faraday cage. All right, now it has thickness, and then I will tell you what created some issues. But then it shows us the following solutions. And then in all of the solutions, with the exception of one, the outside shell of the Faraday, usually Faraday cages are metals or screens that they have, it's like the one that you have in a microwave oven. That's like kind of a Faraday cage, screen that stops the microwaves from coming out. Okay. And then it shows that in the outer, which for me, I took it, this is only one layer of charge, but I will tell you my thinking as well. And then negatives here. And then everything else has a negative or a positive charge. So from all of these solutions, the way they are, personally, I assume that there are no other charges that are hidden. And then what I care about is not so much what happens inside, but what happens outside. Because outside, for a Faraday cage, everywhere, at least far from, all right, usually Faraday cage is like you put them in there and then you go further away and you measure. So we have that E is 0. When can I have an electric field that is 0? Yes. When I have a charge, a positive and a negative charge that are close enough. The only charge from the outside, I don't see this.
Testing.
When I place the Faraday, thank you so much. When I place the Faraday cage, the only thing that I see is the Faraday cage and the charges on it. All right? Yes.
The problem they were having was they thought the positive charges were in the inner shell, inner side of the shell, and the negative side would be on the outer shell because the negative repels the negative charge, and the positive would attract it. So they thought the inside the shell would be all the plus side.
Let's assume what I'm saying is that what I'm saying to that thought is the following. Let's assume that this is a thick metal, all right, like a cylindrical, a cylinder or a sphere that has very thick metal. And let's assume that indeed you have here, I will put it on the here positive. And then outside here you have negative. All right? All right? The problem that I have with that personally is that that's not anymore a Faraday cage. Because if I am outside, the Faraday cage means that when I go outside, I should see as small of an electric field as possible, not this one anymore. But if I have this distribution, then I will see this kind of electric field. All right? I will see that because these are the charges on the outside shell. So that's not a Faraday cage. At least that's how I understood the problem. To be a Faraday cage, you need to have an equal number of positive and negative charges in close distance. Yes? You know what? It can induce its own electric field, but that would be possible if your source was outside. I don't have any other outside sources. See what happens? So if my source was outside, and then I had something like the negative that would induce an opposite electric field, the two could cancel out. But my source is inside. If I have these negative charges outside, there is nothing outside. These are the only ones, and they are going to create an electric field. See? Let me ask you this problem. Forget about that for a moment. What is going to happen? Forget about all of this the problem. Let me ask you this following question. I have a cylinder, a sphere. I have a sphere, and I put on this sphere negative charges. What is going to happen? What is going to happen? Outside of the sphere, obviously. This is a metal sphere, right? Everything is zero in here. But I force electric charges on the outside, they're all negative. So what are we going to see? We'll see this electric field that will end on these charges here. All right? This is not any different from the outside. This is not any different than D. But then that's not a Faraday cage anymore. Yes?
For C, the negative charges and positive charges on the outer shell, don't they form any belt lines outside of the shell?
Yes, but they will cancel out, assuming that the dimensions are not very large. All right? So, yeah, but it's a Faraday cage is going to have a Faraday cage is something that in the far field needs to stop this from being excited. And so if you put this around it, let me go back to the other one. So if you have a charge here, in the beginning it will go like that, the lines. Okay, let me do the lines here. And if you put a cylinder like this, and then you have positive here and negative here, then you're going to have these kinds of lines here, and they will be equal all right? And then they will come here. And practically, what you're going to see is going to be lines going like this. All right? But as these lines go far away, you're going to see less and less of that, which means it's going to be much weaker than this one, because the lines are going to remain very close to the surface. I know that the problem, the weight was given to us. Maybe I can find another problem that is a little more defined. Yes? No, it's like, so here's how it goes. A Faraday cage, well, first of all, to be able to to understand the Faraday, well, let me start with this. Let's assume this one is different from the previous case we had. Why? Because in the previous case, we had a field like this. All right, and practically this field comes out of ideally, all right, if it's like that, out of a plus Q, minus Q. And in this particular case, you have only Q. Let's assume that you have only one, the minus Q there. All right? Not the 2 that you have here. Not the 2. This is the difference between this problem placing a slab and this problem placing another slab. All right? So that's probably the best way to show it. And so maybe let's do the Q here, minus. Okay, do we agree with this? So this is how this is going to go. If it's an infinite slab, uniform charge, all right, it's going to go like this. Okay. Let's assume that we place a metal here. So a real Faraday cage says that we are going to have a E field here, 0. And because of that, we are going to generate charges, Q, in fact, minus Q. And those charges will have to be negative, so the electric field here is going to be 0. And they will be displaced, all right, from positive charges. Now, the positive charges that are going to be created are not necessarily going to be all collected here. As a matter of fact, when you start looking at how an electric field goes inside a conductor, the value of the electric field goes like that inside the conductor, and the same way goes the value of the charge. So what is going to happen is that there is going to be a distribution of positive charges here, but it will never reach the other side. So eventually, yes, they're going to all be crowded here if there is nothing else on the outside, all right? It's not like that. They're going to all be all of the negatives will be here, and the positives will distribute down here, but they will never reach the outside shell to be able to radiate anything, to create a field. But it's better to see it when we look at fields inside conductors, where you see where the field goes. In this particular case, I have to say, the problem seemed simplistic, but if you start thinking more intensely about the physics, yeah, it was a little too simple maybe. What I was going to do when we start looking at currents inside conductors, which we're going to go later in the next chapter, then I will try to bring this problem back to be able to solve it then, okay? Where if we do this? Yes? Yes?
Faraday did an experiment like this called the ice pill experiment, and its outcome was still B or D.
D or? So the outer shell here, you said, had what? So it creates Q. I cannot hear you. But come after the class to discuss it. So, okay, wait a second. What I suggested we do is that we still have left the image theory. We're going to cover it next time before we go to chapter 2. And then send me your comments if there is anything. I will try to be a little more clear about this, and then for next time, or I will give it to you, I will put it on Canvas, all right, and discuss it.